Oh my God. Okay, let's go ahead and get started now. Sorry for taking a little long there. I was trying to get my dogs back in the house and they decided to bark at something. Anyway, we're going to continue our discussion today on chemistry in chapter 2. And we still have a ways to go in this before we have any kind of test. Lab this afternoon, if you're in lab today, we're going to look at diffusion and osmosis, and we're going to look at cells and the cell cycle, and mitosis and cell division. So let's see. Okay, I thought I let everybody in. I don't see anybody else on my list. And I have nobody in the waiting area. So I've got, no, I'll keep an eye out, but I've got 21 people already in. So, okay. Let's go ahead and get started then. I am going to go ahead and open up share screen and go into this. Okay. I think this is close to where we stopped on Tuesday. And when we take a look at, I'm assuming everybody can see the screen because we've had some issues with Zoom on that. Okay, so if we're looking at, there we go. That's how I want to start. Every atom is identical to every other atom, at least as far as its components go. And if I said this today, it doesn't have to hear it again. Every atom is going to be identical to every other atom by its basic components. Every atom is going to have a proton. Every atom is going to have an electron. The only atom that doesn't have any neutrons is hydrogen. Hydrogen has no neutrons, but all the other atoms do. From helium on, we have neutrons. So essentially, the three subatomic particles that we encounter in every atom are going to be protons, neutrons, and electrons. The arrangement of the protons, neutrons, and electrons determine the properties of the individual atoms. That's what makes the elements unique. The elements have, an element of gold. An atom of gold has a combination of protons, neutrons, and electrons that is different from an atom of silver or an atom of carbon. It is the arrangement, it is the number and arrangement of the protons, neutrons, and electrons that determines what type of element the atom's going to be. And every element has all the atoms in an element are going to be identical. They're all going to have the same number of protons. An atom of gold has the same number of protons for every atom. It has the same number of electrons for every atom. Now it can have some fluctuation on the neutrons, but every atom of gold will have the same number of protons and electrons. And there may not be any variations on the neutrons, but there's always a possibility. So protons and electrons are always equal to each other. Every atom of every element, an atom of carbon has 6 protons and 6 electrons, always. Oxygen always has 8 protons and 8 electrons. Carbon, carbon has 6 protons and 6 electrons. Nitrogen has 7 protons and 7 electrons. Those don't change at all. Sodium has 11 protons and 11 electrons. Every sodium atom will always have 11 protons and 11 electrons. And the combination of neutrons doesn't follow a set pattern. Where the protons and electrons are a sequential pattern, the neutrons can be variable. So anyway, if we're looking at the different elements, again, the elements are made or determined by these subatomic particles. Hydrogen, 1 proton, 1 electron. Helium, 2 protons, 2 electrons. Lithium, 3 protons, 3 electrons. And that is consistent all the way across all the elements. You're never going to have an atom of gold with just 6 protons and still be gold. Doesn't work that way. There is consistency here. Now, the first number that we pay attention to when we're looking at the periodic table, for example, of an atom is its atomic number. The atomic number gives you the number of protons in the nucleus of the atom. And there's a reason for all this, and I'm going to try and keep it as interesting as I can. There's a reason we go through this part of it here in our discussion. This is pretty dry, I will admit. But this is not a general chemistry class. This is A&P, and so I'm going to try and keep it as focused as I can on our healthcare perspectives. Why are we all in this A&P class? So the atomic number gives you the number of protons in the nucleus, and it gives you the number of electrons in orbit around the nucleus. We're going to see that the electrons are really, really important. Electrons are small. They have no weight, no mass, but they have a charge that is equivalent to the proton. The proton and the electron balance each other out, positive to negative, negative to positive. Of course, the proton has this massive weight of 1 atomic mass unit, whatever that is. It is, remember, they say it's an arbitrary unit. So, and the electron has no mass. So the atomic number is the number of protons and also the number of electrons. Those protons equal electrons. Electrons equal if the atomic number of carbon is 6, that tells you it has 6 protons and 6 electrons. If the atomic number of sodium is 11, it has 11 protons and 11 electrons. If the atomic number of chlorine is 17, 17 protons, 17 electrons. Now, the mass, and that number is usually on the periodic table, is usually printed above the symbol for the element. So if it's calcium, Ca, above calcium will be the atomic number, whatever calcium is. I don't remember off the top of my head. But how about carbon? Carbon is 6, or oxygen is 8. So you have 6 protons in carbon, 8 protons in oxygen. Carbon has 6 protons and 6 electrons. Oxygen has 8 protons and 8 electrons. Hydrogen has 1 proton and 1 electron. The atomic number is above the symbol. The mass number is underneath the symbol on the periodic table. Forget what it says here about subscripts and stuff like superscripts, things like that. The mass number on the periodic table is underneath the symbol. The mass number is the sum of the number of protons and the number of neutrons. Carbon, for example, we have atomic number 6, tells you there's 6 protons. The mass number underneath it is 12. Well, in this case, carbon has 6 protons and 6 neutrons. That gives you a number 12. Oxygen has a mass number of 16. It has 8 protons, 8 electrons. It also has 8 neutrons. You add up the number of protons and neutrons, and you get the mass number. And we use, for our purposes, we use mass number and atomic weight interchangeably. We go back and forth in this all the time. So we just say, what's the weight of an oxygen atom? 16. 8 protons, 8 neutrons. We don't get too hung up on between mass and weight as far as our concerns. So atomic number and mass number. The number underneath the symbol is the mass number, and the mass number is simply the number of protons and the number of neutrons added together. It can be 12, it can be 14, it can be 3, whatever the total number of protons and neutrons are in the nucleus is the mass number. Now, when we look at an atom as if we could see one, because they are extraordinarily tiny, we know that protons and electrons are balanced. Now, there are 2 models to explain where these subatomic particles are located. Protons and neutrons and electrons are the subatomic particles. Work that into your conversation over the weekend, and people will be amazed and impressed when you say, "Oh, subatomic particles." Right? So we do know that the protons and neutrons are found in the nucleus of the atom. The nucleus of the atom is in the center of the atom. That's its only similarity with the nucleus of a cell. Cells have a nucleus in the center, and that's where the DNA is located. That's the only thing that they, location is what they share with, with atoms. Because the center of the atom is the nucleus, the center of a cell is a nucleus. That's the only similarity at all. But there are 2 models that show how the nucleus looks and where the electrons are. Because remember, the electrons now are moving at the speed of light, 186,000 miles per second, which we cannot grasp how rapidly that is. It's the speed of light. Light moves so rapidly, at 186,000 miles per second, we can't comprehend that. I mean, think about it. Even at that speed, the sunlight striking the Earth left the sun 11 minutes ago. The sunlight that's hitting the Earth right now took 11 minutes to go 93 million miles. Only 11 minutes. It's still pretty impressive. Anyway, 2 models, the planetary model and the orbital model. The planetary model looks like one of those charts of the solar system we saw when we were in school. It has, where you had the moon going around the Earth and the Earth going around the sun and stuff like that. It shows the nucleus in the middle and the electrons in orbit around that. Usually shows the nucleus as a ball, just one solid ball, and that's the nucleus of the atom. And it has 1 or 2 or a half a dozen electrons spinning in various shells or orbits around the nucleus. The only thing wrong with that is that the electrons move so fast, you don't know exactly where they're located. They're moving so rapidly at the speed of light. They're moving so rapidly, you can't tell. So the orbital model, which is much more accurate in its own way, shows a fuzzball, a cloud around the nucleus. So you see something that looks like this. This is the planetary model on top, where you have the nucleus in the center and the electrons in orbit around that. The reality of it is that we have protons and neutrons in the nucleus, and we have this cloud of electrons here, like this in this illustration here, moving so rapidly, because we can't get a picture of something moving at 186,000 miles per second. At least not yet. Even the fastest cameras can't get that. So, but do we really need to know that the electrons are moving around like that? It doesn't really matter to us. We know that we know that an atom has protons, neutrons, and electrons. When we visualize an atom, we tend to visualize the planetary model, if we think about it at all. I can't tell you the number of times someone has come up to me and said, quick, draw a picture of the planetary model of the atom carbon. That's never happened. So what's more important is to understand what these atoms do in our bodies. Why are they important? So, because we're not talking chemistry just to talk chemistry because it's mandated by the state for A&P classes. No, we're talking chemistry for a reason. Because our bodies are based on chemical reactions that take place all the time. And all of our physiology, anatomy is structure, physiology is function. All of our physiology is based on all these chemical reactions taking place constantly. And we need to always understand what causes those reactions to occur. What are those reactions indicating? Is everything homeostatic, or are there some sort of pathological condition developing that we can detect from the results of chemical reactions? I mean, consider this. I have said to you several times, and I'll probably keep saying it, that the reason that we breathe faster after exercise is because of an accumulation of carbon dioxide in our blood. When we burn carbohydrates for energy, we release carbon dioxide. Now, our brain can't monitor carbon dioxide. It doesn't need to. Our brain monitors the change in pH, a change in acidity in our blood, because the carbon dioxide goes into solution in our blood plasma and forms carbonic acid and makes our blood plasma slightly more acidic. And so it's easier for the brain to monitor the change in acid or base levels in our blood than it is to try and monitor CO2 levels everywhere. Because our blood circulates throughout our bodies every 20 seconds. So all we got to do is monitor the pH levels, the acid levels in our blood. And so the brain says, we're getting more acidic. Let's breathe faster because we better blow off that CO2. And that's great because that works nearly every time. It works nearly every time you exercise, you work out, you run up a flight of stairs, you're breathing hard, and because you're blowing off CO2, not because you need oxygen. You've got plenty of oxygen in your blood, but it's to get rid of the excess CO2. And that works great, except if your patient is diabetic. You have a patient that's diabetic and breathing rapidly. Now they're just sitting there and they're breathing rapidly. They haven't run anywhere. Why are they breathing rapidly? Do they have a CO2 problem? It turns out that the patient in a condition known as ketoacidosis, which we'll talk about in AP2, if a patient is diabetic and their cells are starving because they're not producing enough insulin, their blood glucose levels are through the roof, their blood sugar levels are skyrocketing, but it's not getting into the cells because their insulin doesn't work or they don't have enough insulin, one or the other. Our bodies will start breaking down fats. Our bodies will assume that we have no food, that we have no glucose, no sugar, and we'll start breaking down fat to make sugars. We can convert fats into sugar and use that for fuel. And so our bodies will start breaking down fats. When you break down fats, you release fatty acids. And those fatty acids make the blood more acidic. And the brain assumes because of the pH, the acidity levels are rising because we're becoming more acidic. Oh, we must have exercised. I better breathe fast. So there we're getting thrown a curve because your patient hasn't exercised. They haven't done anything strenuous, and yet they're breathing like they have because the brain is assuming that they have, and that's because of carbon dioxide. So they're breathing fast to blow off the CO2, which doesn't exist in this case. This is a chemical reaction. And we need to understand how chemical reactions occur in the body and how they can sometimes be different and change. So, and that's why we're talking chemistry. I know this is not the most exciting stuff, but there is a reason for it. So, okay, moving on. Orbital model, planetary model. Think which one you ever, it doesn't matter to me, planetary model works. It's the simplest, it makes it probably easier to understand. That's what I'll end up using talking about chemical reactions anyway. The reality is that since the electrons move so fast, it looks more like the fuzzball, but that's not really going to help us in our understanding in healthcare. So let's take a look here at our very smallest atoms. Using the planetary model, we can see the location of the protons, the neutrons, and the electrons. If we could take a snapshot of a real atom, we'd show this, but again, the electrons move too rapidly. So here's hydrogen, first one on the left. One proton, one electron. The electron is in orbit around the nucleus where the proton is found. There's nothing in the nucleus except the proton, but that's still the nucleus. The electron is in orbit around there. The middle one is helium. 2 protons, 2 electrons. It also has 2 neutrons. So the nucleus of a helium atom is going to have 2 protons and 2 neutrons. It's going to have 2 electrons in orbit around the nucleus. And they're not going to run, we don't know where they're going to go. They're in orbit around the nucleus. They're all over the place, but they're in orbit around the nucleus. And the distance from the nucleus never changes significantly. They may be moving, they may form a fuzzball and fuzzy cloud approach, but the distance they stay from the nucleus remains fairly constant. So the distance stays fairly constant. So while they are moving at the speed of light around the nucleus, the distance they are from the nucleus is pretty consistent. So, this is while it's simplified, it's accurate in showing that the electrons stay in this first orbit out here about the same distance, even when they're using that cloud approach. They're the same distance. Same thing applies here in lithium. Well, lithium has 3 electrons. It has 4 neutrons, so it has 3 protons. The nucleus has the 3 protons and the 4 neutrons. Something different here with lithium. It has 2 of its electrons in its first orbit, but it has a second has the 3rd electron in a second orbit. Because apparently there's a rule in chemistry that there's a rule for atoms. Atoms don't put more than 2 electrons in their first orbit. They only put 2 in their first orbit, and then they start filling up the next level up, the next orbit. And so lithium has 2 electrons in the first orbit and 1 in the next orbit out, the second orbit, if you will. And the further along we go, looking at our various atoms, the atom with 4 protons will have 4 protons and 4 electrons. It will have 2 protons in its first orbit and 2 in its second orbit. The next atom with 5 has 2 electrons in its first orbit and 3 in its second orbit. Number 6 is carbon. Carbon has 2 electrons in its first orbit and 4 in its second orbit. And this process continues. As we add more and more electrons, as we add more protons, we add more electrons. And as we add more electrons, we have to put them in different orbits. We can only put 2 electrons in the first orbit. We can only put up to 8 in the second orbit. So we start filling up these orbits. Now, while protons and electrons are evenly balanced, neutrons are variable. Neutrons can fluctuate in nucleus. We have a compound known as an isotope. The isotope will have every isotope atom of anything will have the same number of protons, the same number of neutrons, but it will have a different number of neutrons. So the same number of protons, same number of electrons, but it may have a different number of neutrons than most of the other atoms of that type. So for example, carbon has 6 protons. Carbon has 6 electrons. Most carbon atoms have 6 neutrons. The atomic mass underneath the symbol for carbon, the letter C, says 12. Okay, so 6 protons, 6 electrons, 6 neutrons, atomic weight is 12. But some versions of carbon have an atomic weight of 14 because it has 8 neutrons instead of 6. An atom that has a different number of neutrons than most of the other atoms of that nature is unstable. Carbon-12 is stable. The most common version of carbon has 6 neutrons. We say that the atomic weight of carbon is 12. Okay, 6 protons, 6 neutrons. 6 neutrons is what most carbon atoms have. But there is a variation called carbon-14 with 8 neutrons, and it is unstable. It's radioactive. Isotopes are the unstable version or the radioactive version of a particular element. If you add a neutron to a stable atom, you make it unstable. You can make it radioactive. But radioactivity means that an unstable atom will give off radiation. Why? Well, let's take carbon-14, for example. It occurs naturally. Carbon-14 occurs naturally. It has 6 protons and 6 electrons. It has 8 neutrons. It's unstable. Carbon-14 will try to make itself stable by degrading or breaking down. It will start kicking out alpha particles and beta particles and gamma rays. This energy, they'll release it in the form of energy. This energy is the glue that holds the extra neutrons in the nucleus. By kicking out the energy, eventually a carbon-14 atom can kick out a neutron. And when it can kick out a neutron, it gets more stable. And so we want to get stable. The atom wants to become stable. A carbon atom wants to be stable. It's not stable if it has extra neutrons. So it will gradually release energy And when enough energy gets released, it will kick out a neutron. And that atom will go from carbon 14 to carbon 13. And then it will kick out more energy and kick out another neutron. And then it will be at the stable version of carbon, it's carbon 12. So again, why do we care about radioactivity? Well, take a look at this. This is 2 isotopes of hydrogen. There's hydrogen on the left. Chemists would call it protium, but we're going to call it hydrogen. 1 proton, 1 electron, no neutrons. But here we have a variation on that. We have an isotope of hydrogen called deuterium with a proton and a neutron in its nucleus. Still 1 electron. Protons and electrons haven't changed. This thing is heavier. Instead of an atomic weight of 1, it has an atomic weight of 2, which doesn't seem like a big deal, except that deuterium, when it combines with oxygen, forms something known as heavy water. And heavy water is used around nuclear reactors to absorb neutrons. It's more dense than regular water. So this is, we call it heavy water, causes the hydrogen to weigh more. Now the third version here is called tritium. Tritium has got 2 neutrons in the nucleus. So it has an atomic weight of 3 instead of 1. Still has 1 proton and 1 electron, but now it's heavy, even heavier than deuterium. So this is an isotope, and it is, these isotopes are unstable. They will degrade and try to kick out those extra neutrons. That's what they do. And so why do we care? Well, this radioactive decay occurs at a constant rate. It doesn't fluctuate. If you have a radioactive carbon atom, it will release energy at a constant rate until it can kick out a neutron. If you have a radioactive element of anything, it will release energy at a constant rate, a measurable constant rate. And now we find that we have a use for that. Radioisotopes in healthcare work for us. Knowing that we can use isotopes to test and evaluate patients. Consider that in our bodies, we have a gland in the middle of our neck called the thyroid gland. The thyroid gland produces thyroid hormone, clever name for the hormone. Thyroid hormone regulates metabolic activity. In other words, it regulates all the chemical activity in our bodies. Every cell gets exposed to thyroid hormone. If we have an overactive thyroid, we say we are going to have hyperthyroidism. We burn up calories at a faster rate. We are overactive. We are easily agitated. We have an elevated heart rate, elevated breathing rate. We are let's just say we're unpleasant to be around. And it can become a life-threatening situation. A hyperactive thyroid can cause significant health problems. They can ultimately lead to some sort of neurological impairment or even death. Okay, so it's not a condition we want to be in. We can also be the other way. We can have a hypothyroid activity where our metabolic rate is so low that we're always cold, we're sluggish, we're constipated, we're puffy, we swell up, not from being constipated. And it's just, again, because our cells are not getting this thyroid, are not getting enough thyroid hormone to to control all of the chemical reactions in our bodies. It seems that thyroid hormone depends on the presence of another element known as iodine. Thyroid hormone doesn't get made unless we have iodine present. Okay, so if we suspect that our patient has a thyroid issue, we can administer a low-level radioactive dose of radioactive iodine. Iodine will only go to the thyroid. It's the only place, the only cell in the body that takes up, only cells in the body that take up iodine are in the thyroid gland here in the neck. Iodine combines with another molecule in the thyroid gland to form thyroid hormone. And if it's radioactive, it will glow on a scan or on an X-ray. And here we have, because soft tissue doesn't show up well in X-ray. But here we have an example of a thyroid scan with using radioactive iodine, showing you where an area of the thyroid gland isn't working. This dark area indicates there's something there. Something's going on that it's not functioning properly. And that may be affecting the thyroid, because it's not the kind of, hey, how about a thyroid scan? I've got nothing else to do today. That doesn't work like that. You wouldn't have a scan unless there was a suspicion that thyroid hormone levels were, not working right. Either too high or too low. And so this dark area tells you that portion of the thyroid isn't working. We can also use, now how long does the radioactivity last on a test like that? Hours. The half-life of the radioactive iodine, half-life is how long does it take for half of the energy to be lost? The half-life might be 6 hours. So in 6 hours, the radioactive energy in an iodine atom is cut in half. And in 6 more hours, it's cut in half again. And in 6 more hours, it's cut in half again till it's gone. So in about 24 hours, you're no longer radioactive. You no longer glow in the dark. Some elements have a half-life of several days. Certain elements have half-lives in the thousands of years. Carbon-14 has a half-life of 5,000 years. That's the estimate anyway. So why do we use it? Well, for a short term, we can test. If you've ever had a thyroid scan, you've probably used radioactive iodine. There are radioactive tracers used in the test for gallbladder activity. You can use radioactive isotopes to treat various cancers. So there are a lot of possibilities that these isotopes provide for use in healthcare. Okay, so that's the difference. While everybody has protons, neutrons, and electrons, the neutrons can be variable. And if the number of neutrons is different than what the most common version of that element is, then it's likely an isotope, and it's likely unstable. Because we're going to try to get, and atoms always want to be stable. Okay, so moving on. Atoms like to combine with other atoms in a chemical reaction. We make molecules. We combine hydrogen and oxygen to make water. The end result of that kind of chemical reaction is a substance called water that is different from oxygen and different from hydrogen. It has different properties. Hydrogen and oxygen alone have different unique properties that are not present when they're combined to form water. Carbon and hydrogen and oxygen have properties that are different if you combine them to make sugar. Sugar is a totally different compound, totally different molecule than the individual molecules of carbon and hydrogen and oxygen. So atmospheric oxygen that we breathe is different than elemental oxygen. Totally different properties. Atmospheric oxygen is called O2. It takes 2 atoms of oxygen for the oxygen and to form O2, the stuff we breathe, as opposed to elemental oxygen, which just has O. Okay. Molecules and compounds. The term here is a molecule has 2 or more atoms of the same type bonded together, like 2 oxygens or 3 nitrogens. Compounds are different atoms chemically bonded together, like glucose, C6 6 carbons, 12 hydrogens, 6 oxygens. But we tend to use the term interchangeably. We say a molecule of water, a molecule of glucose. We just treat them as molecules. They are the product of chemical reactions. And chemical reactions make a chemical change to the product. Combine hydrogen and oxygen, you get water. Water is different from individual hydrogen and oxygen. Carbon dioxide is different than carbon and oxygen. There's been a chemical change here. Most matter, however, doesn't go through chemical changes. Most matter occurs as through physical changes. So only chemical changes alter, give you a different product than you started with. When you have a chemical change, you can't take the product and filter out the components. You can't take water and run it through a filter and physically separate oxygen and hydrogen. You can't run sugar through a filter and separate out the carbons and the hydrogens and the oxygens. You can't take, I'm gonna repeat myself, carbon dioxide. You can't filter the carbons and the oxygens out. You can't filter out the 2 oxygen atoms to make elemental oxygen. That you can't physically separate them because they're joined together chemically. It's a chemical reaction. You have changed their properties. Mixtures, however, you can filter them out anytime. You can take concrete and break it apart into its smallest particles and get the sand and the cement and the gravel out of that, because it has been a physical change, but not a chemical change. The physical change occurs when you combine all the ingredients together. That's a physical change. Most matter is put together in physical changes. You could take asphalt on the road and break it and physically separate it out because it's not a chemical change. Mixtures of any kind are never a chemical change. Now we have 3 types of mixtures. We have solutions, we have colloids, and we have suspensions. A solution is what we call a homogeneous mixture, meaning it is every part of the solution is identical. Usually they're transparent. A Coke a bottle of Coke is a solution. You look at it, you can see through it, even though it's caramel colored. You can see right through it. You can see through a Mountain Dew. You can see through a Sprite or a 7-Up. You can see through tea. You can see through coffee. You can take the coffee and run it through a filter that is small enough that could separate out the coffee particles from the water. If there's creamer in it, you could separate out the creamer from the coffee and from the water. Mixtures can be separated and solvents can be separated. If you have a solution is made up of a solvent and a solute. A solvent is the dissolving medium. It is usually, in our bodies, it is usually always water. The solvent is what dissolves the solute. Now, sometimes the solvent is air, atmospheric air around us. That's about 79% nitrogen, about 20% oxygen, and then you got carbon dioxide, methane, and all the other trace gases thrown in there. That's a solution. It's transparent. If you look around your room, you can't see anything in the air. It is clear, it's invisible. And yet we have nitrogen, we have oxygen, we have carbon dioxide, we got methane. We don't like look in the corner. Oh, look, there's methane in the corner. Stay away from the methane. Oh, carbon dioxide, get away from that. Oh, there's some oxygen, I'll breathe that over there. It doesn't work that way. It's all transparent. just like a liquid. Now, in our bodies, most chemicals are dissolved, or rather, all chemicals are dissolved in solution. Water is considered the universal solvent. So the solvent is the dissolving medium. The solute is what gets dissolved. If you're going to make sweet tea, you're going to take hot water, you're going to put your tea bags in the hot water, you're going to throw your sugar into the hot water because we know it goes in better in hot water. And when you're done, you're going to have sweet tea. And when it cools down, you put it over ice and you drink it. Now, it's transparent. I mean, yes, it has the tea pigmentation, it has the coloration from the tea, but you can still see through it. And it tastes sweet. And if you have filters of sufficient size, you can filter out the sugar. You can filter out the tea and have the water left behind. And the water will be clear and transparent. You filtered out all the components. The solute particles can always be filtered out. Doesn't matter how small they are. There are filters that you can get for camping that will filter out everything. You can suck water up out of a muddy stream with bacteria and viruses in there, and it will filter out all of that. You can drink the pure water on the other side of the filter. And it works because it's all about particle size. So when we look, we can make solutions up all the time. We can take sugar and throw it into a beaker of water. We can throw salt into a beaker of water, and we don't see the salt, we don't see the sugar. And yet, the two beakers are transparent. They look identical. You can't tell them apart. If you had a third beaker filled with nothing but distilled water, they would all look the same. They won't look different because the solutes are all in solution. They're invisible. They are a homogeneous mixture, meaning that they are the same mixture. In our bodies, blood sugar shows up in our blood plasma. The plasma is the liquid portion of our blood. It's what the red cells and white cells and platelets float in. The plasma is where sugar goes when we eat something. Blood goes into our plasma. The sugar goes into our plasma. We can measure that. We can filter it out. The glucose, the sugar, is our solute, and the plasma is our solvent. So, like most things, we use solutions all the time. When we breathe air, before that oxygen can go across the membrane from our lungs into our blood, it has to be combined with it has to go into a layer of water that lines the inside of our lungs. The oxygen dissolves in the water, and then it moves across the membrane of the lung cell into the capillary. We dissolve the oxygen into water lining the inside of our lungs first, and then it goes in the blood. Carbon dioxide, which is in our cells, has to go into a layer of water in the lungs before it can be released to the outside air. So we're making solutions up all the time. Okay, so here's an example. Take sugar, add it to a beaker of water, add water, and mix it up. Sugar disappears. Add salt to a beaker of water, and the salt disappears. The sugar is dissolved. The sugar is the solute. It's dissolved in the solvent, which is water. The particles are evenly distributed here. And you don't see them, but they're there, but they can still be filtered out. That's the thing about these mixtures, is that mixtures can always be filtered out, whether it's a solvent, whether it's a solution, or a colloid, or a suspension. Now, solutions. Our bodies use solutions all the time. In healthcare, we hang IV lines. on your patient, and run a line into a vein, and they're getting normal saline, for example. Salt water that has the same consistency of plasma, it's going in. It's used as a pathway for other medications. So you would pay attention to solutions like this. You would never give your patient distilled water. You would always use normal saline, because in the solution in the IV bag is the same as the solution same as the plasma. So there won't be any recognized any different. So how do we measure solutions? Well, it's a really easy process. And this is where, again, there's a healthcare perspective on this. It's percentage. It's percent. The percent of salt in normal saline is about 0.9%. So your IV bag of normal saline is going to be 0.9%, which just happens to be the same percentage of salt in our plasma. Percentage, how do you make a percent solution? Well, if you want to make a 10% salt solution, you would take, in a liter of water, you would take 1 liter of water and add 100 grams to that liter of water. This liter of water is 1,000 milliliters. You want to make a 10% solution. What's 10% of 1,000? 100. And so 10% of 1,000 is 100. So you want to add 100 grams of sodium chloride, or 100 grams of sugar, whatever 10% solution you want to make. Let's say it's salt. You add 100 grams of sodium chloride into a liter of water, and that's 10%. Or you want to make a 20% salt solution, you would add 200 grams. You want to make a 40% sugar solution, you would put 400 grams of sugar into a liter of water. So it's really that straightforward. The solvent is in healthcare, the solvent is nearly always water. And you just base it off of a liter. And it's however many grams you need to be 20% of a liter, 40% of a liter. It's very, very straightforward. And when we have labs on the ground, we do this kind of stuff, do these kind of activities all the time, where we have solutions that we've made up ahead of time for you. Another way we look at solutions is through a measurement known as milligrams per deciliter. A deciliter is 1/100th of a liter. We use this term to measure blood sugar. When you have your fasting blood work done, we've all done that. We've all gone in early. We always try to go to the lab early in the morning so we get our blood work done early so we can go eat something afterwards. When we have fasting blood work done, we're getting our blood sugar levels measured. And the term is milligrams of sugar per deciliter. Now we like to see anywhere between 80 and 100 is a nice number. We like to be below 100 of that. Elevated blood sugar may be let me rephrase it. Consistently elevated blood sugar may be an indicator of a problem with developing diabetes. And you'll see that in some cases your diabetic patient may present with a blood sugar of 600, or more, whereas most healthy individuals are going to have a blood sugar somewhere below 100. That's the standard right now, below 100. So how do we measure it? We measure it in milligrams per deciliter. And in general, we just we focus on the number. We're not going to when you're charting the information, the milligrams per deciliter is nearly always going to be written on the chart already. You just write down the number because we're focused on the number. We're not focused on it's understood that it's milligrams per deciliter. The third term that we use in solutions is called molarity. Deals with moles, and we're not talking those little animals that crawl through our gardens. A mole is definitely a chemistry term. Molarity is the number of moles of solute per liter of solvent. And there's one good reason that I talk about this. A mole of any molecule, of any compound, is the molecular weight of that particular molecule expressed in grams. For example, 1 mole of glucose. 1 mole of glucose. Glucose has a molecular weight of about 180. If you take the 6 carbons, the 12 hydrogens, and the 6 oxygens, and add up their atomic weight for each one, carbon is 12. So you have 6 carbons, that's 6 times 12 is 72. 12 oxygens, and 12 hydrogens, that's 12 because the atomic weight of each hydrogen is 1. So 72 plus 12 is 84. And then you've got the 6 oxygens at 16, and that is 96. And 84 and 96 is 180. Oh, wow, I did the math right in my head. I should stop for the day at this point. No, but if you add up the individual atomic weights of all the atoms in the molecule, in the case of glucose, it comes out to 180. If you want to make a 1 molar solution of glucose, you would put 180 grams into a liter of water. And that's a 1 molar solution. If you wanted to make a 1 molar solution of sodium chloride, table salt, well, the molecular weight of salt is 58. Add the atomic weight of sodium and the atomic weight of chlorine, and that's 58. So if you had 58 grams of table salt in a liter of water, you would have a 1 molar salt solution. We don't use this very often. Chemists use it all the time, particularly in dealing with acids and bases. They use 1 molar and 2 molar and 6 molar. Acids that are 6 molar, based on 6 molar solutions, are very strong. Acids that are like 0.01 molar are very weak concentrated. It can still be sulfuric acid, but it can be a very weak solution of sulfuric acid. So we don't need to worry about that unless you're going to work in a laboratory setting. But the only reason that we pay attention to molarity is that the number of solute particles, the number of particles in solution in any mole is always going to be the same. A 1 molar solution of sodium chloride will have 6.02 times 10 to the 23rd molecules of salt. So a 1 molar solution of sodium chloride, molecular weight 58, 58 grams of salt into a liter of water, it will have 6.02 times 10 to the 23rd molecules of salt. A 1 molar solution of glucose, molecular weight 180, will also have 6.02 times 10 to the 23rd molecules. We call this number Avogadro's number. Circle that on your notes, star it, and say, don't forget this number. Because I guarantee you'll see it later at test time, whether here or on the final. Now, chemists get real excited about Avogadro's number. In fact, they celebrate Avogadro's Day on October 23rd. Some chemists even get up at 6:02 in the morning to celebrate. Hey, it's Avogadro's Day. It's 6:02 a.m. on October 23rd. Well, biologists don't get that excited about it. We don't even celebrate Pi Day. March 14th, 3.14. So the reason we pay attention to Avogadro's number is that the solute particles in solution drive the movement of water across the membrane. And that explains osmosis. Avogadro's number dictates that the number of solute particles per mole are going to be exactly the same, but the number of particles, and that's true. So depending on the strength of the solution on one side of a cell membrane to another side, the number of particles on one side will drive the movement of water one way or the other. And we'll see, and if you haven't heard it yet in lab, the term osmosis is a term describing movement of water across cell membranes. And the rule of thumb with osmosis is that in osmosis, water moves from high water to low water across a membrane. Because if you have high water concentrations, you have low solutes. And if you have low water concentrations, you have high solutes. And water always goes from the high water side to the low water side. Now, that's a lot to throw at you, so let's let it go, and we'll talk a little more about it in lab today. Okay, a colloid is an emulsion. A colloid has floating particles in it. Milk is a colloid. The butterfat floats inside the milk. If you have whole milk, which is 4% butterfat, the butterfat particles float in there. They never settle out. They make the solution, they make the liquid opaque. It is heterogeneous. You can't see through it. It's cloudy. So these are colloids, emulsions. Jello is a colloid because it's not completely transparent. You have the mixture, and you have the substances that are suspended in here and will never settle out. In a colloid, there is no settling. It never changes its state. Milk stays this opaque, heterogeneous mixture the whole time. You can filter the fat out. You can filter out the water. You can filter all the components out. And that's one of the characteristics of a mixture. You can always filter out the parts because there is no chemical change. When you have whole milk, you have fat floating in the watery, milky looking fluid. It doesn't change. So that is a colloid. Now, the last type is a suspension. A suspension will settle out. A suspension occurs when you have particles in some sort of medium, like water, that will, when they're mixed up, they will fill up the water column, if you will, fill up the beaker, the solution, the cylinder, whatever, and then the particles will settle at the bottom. Consider if you're going to set up an aquarium and you put in a layer of sand in the bottom of the aquarium, you get like 6 inches of sand, a lot of sand in there. It's a big aquarium. So then you add 30 gallons of water. And the water goes in and all the sand is stirred up, and all the work you did leveling out the sand to make it look nice and pretty is all torn apart because the water just, moved it around. It put it in agitated the sand. The water in the fish tank is very cloudy, but in about an hour, it's clear because all the sand has settled to the bottom. That's a suspension. It goes into the water column and then settles down. Blood is a suspension. Blood, whole blood, is red cells, white cells, and platelets in the plasma. But if you let a sample of blood sit for a few hours, all the red cells and white cells and platelets settle to the bottom of the tube, and the plasma's on top. Or you stick it in a centrifuge for 5 minutes and spin it down, and all the blood cells move to the bottom, and the plasma's left behind. It is also heterogeneous. You can't see through whole blood. You can't see through a cloudy aquarium because it's all mixed together. Consider Italian dressing, salad dressing. Italian dressing has all the seasonings mixed up in the vinegar portion and the oil portion on top. You shake it up and everything's agitated, and then if you wait for a little bit, all the seasonings settle at the bottom of the bottle. The oil moves to the top. Again, a suspension. The everything in there can be filtered out like any other mixture. It can be filtered out. Mixtures don't involve any kind of chemical change. It's a physical change. It's a physical change that you can still separate products out. Again, if you're putting down a concrete sidewalk or repairing your patio or something, what you put down is still going to be, you can still break it apart and get back to the original components. You mix sand and water together, you can still separate them out. Mixtures are only physically intermixed. There is no chemical change. The sand hasn't changed in the fish tank. The water hasn't changed in the fish tank. They may be mixed together, but they will separate out again on their own with no change. The components in a glass of milk are only physically intermixed, and they can be filtered out. The same with sugar water or salt water. You can take a beaker, you can make a 10% sugar solution and set it in and have it in your beaker and let the beaker set out and let the water evaporate, and all the sugar will be left behind because the sugar doesn't disappear. Or you can run it through a filter and filter out the sugar. The same with salt. If you have a beaker of salt water, that water will evaporate and leave the salt behind. If you've ever had a saltwater aquarium, you know what I'm talking about. If you've had a saltwater aquarium, salt accumulates on the edges, on the top edges of the tank, and you have to push it back into the water or scrape it back into the water so it goes in the solution, or just add more water to the tank to keep your salt levels up. Because the water evaporates out of a saltwater tank and the salt is left behind. So mixtures are simple. There is no physical change taking place here. But chemical changes are different. Chemical changes, the product of a chemical reaction is always different than the reactants. What you started with is always different from what you end up with. Baking a cake is a chemical reaction. It is not a physical change. When you bake a cake, if you mix up the ingredients and you bake the cake, you can't take that cake and reverse the process and start filtering out everything. Because you chemically altered the components of the cake. You mix the eggs and the oil and the batter and the flour and the sugar and the salt and whatever else you put. I have nothing about baking cakes, but you mix it all together and then you apply energy to it and you have a cake, more or less. Okay. And what your end product is different from your starting reactant. Chemical reactions are going to be different, are different than physical reactions, physical changes. A chemical reaction occurs because of the presence of electrons in here. A chemical bond that occurs is due to the need to achieve stability and to share energy. A chemical bond is not a physical bond. And a chemical reaction always occurs as a result of the electrons. Electrons are located around our atom in shells or orbitals. I'll use shell and orbital interchangeably from here on out. Every shell that has electrons in there has a set amount of energy in that shell. And electrons in their very first shell around the nucleus are using a tremendous amount of kinetic energy to keep from getting sucked into the nucleus. They stay in orbit, but they're using a lot of their available energy that's pushing them at the speed of light. to keep from being pulled into the nucleus. Because remember, while the charge of the electron is a negative charge, and the charge on the proton is positive, and they're balanced. But in the nucleus, you have all the protons. So let's say you've got carbon. The carbon atom has 6 protons, and they're all in the nucleus. So you have 6 positive charges right there. The 2 electrons that we find in the first shell around the nucleus, just two little negative charges. They have this powerful pull on them from the nucleus. Yes, the charge, 1-to-1, the charges are balanced, but this powerful pull of the nucleus on those individual electrons is very strong. So to keep from getting sucked in, they use most, if not all, of their available kinetic energy to stay in orbit. But the next shell out, the second shell, where carbon only has 4 electrons, because it only has 6 protons, it only has 6 electrons. In its second shell, it has 4 electrons. They don't have to work as hard to keep from getting pulled in. They have some potential energy to play with. They don't have to use all of their kinetic energy to keep from getting sucked into the nucleus. The further out we go, the more potential energy each atom is going to have. First shell of an atom can only hold 2 electrons. If it doesn't have 2 electrons, it still has one. It still only uses the first shell. Hydrogen only has 1 electron, so it puts its only electron in the first shell. Helium has 2 electrons, so it still uses the first shell. Lithium's the first atom to use the second shell. So the first shell can only hold 2 electrons. The second shell can only hold 8 electrons. The third shell can only hold 8 or 18. That's while there are 7 different shells, we're only concerned with the first 3 because elements that are involved in human physiology are only found in the first 3 shells. So this is what the shells look like. This is aluminum, atomic number 13, 13 protons, 13 electrons, 2 electrons in its first shell, 8 electrons in its second shell, 3 electrons in its third shell. The third shell, the outermost shell of any atom, is called the valence shell, and that's the shell that's reacting, because the valence shell will always have the greatest amount of potential energy to combine with other atoms. Now, I'll leave you with this point here. Why do we want to combine with other atoms? Because an atom that doesn't have its valence shell filled up is unstable. Atoms that don't have their valence shell full are unstable and want to achieve stability. So they will do everything they can to get electrons in that outer shell. And the way they do that is they will combine with other atoms to share their electrons or to steal their electrons to achieve stability. So I'll leave you with that thought. We'll start picking up with that next week. No classes on Monday. Doesn't affect our lecture because we're Tuesday, Thursday, but Monday's a holiday. The campus is closed. So anybody that has a Monday class is not going to meet on Monday. So let me get us out of here. And okay, and that's all I want to talk about today. I'm going to stop us here. Lab will pick up at 1 o'clock today, and we'll talk about diffusion and osmosis some more, and we'll talk about mitosis and cell division in the cell cycle. So as far as lecture goes, we're done. I'll see you all next week. Have a great holiday. Try not to think about A&P for at least one day, and try to work subatomic particles into the conversation over the weekend and see how people react. So see you next week.